Hey guys, today we are going to learn 4 different shortcuts that can help us prove that triangles are congruent. In our previous lesson, in order to say triangles were congruent, we had to be able to show that all 3 sets of sides and all 3 sets of angles were congruent. But with these shortcuts, it's going to make this a little bit easier for us. So first, we have the side-side-side congruence postulate. If 3 sides of one triangle are congruent to 3 sides of a second triangle, then the 2 triangles are congruent. So this shortcut cuts our work in half. We don't have to show all 3 sides and all 3 angles, just all 3 sides will do. So if segment AB is congruent to segment RS, segment BC is congruent to segment ST, and segment CA is congruent to segment TR, that is enough to say that triangle ABC is congruent to triangle, and I want to make sure this is in corresponding order, so I have ABC, RST. So here we're given FJ and HJ are congruent segments, and that already has marks, so we've got these congruent sides. And point G, right here, is the midpoint of segment FH. Is there enough information to prove that these 2 triangles are congruent? And explain. So, because G is the midpoint here, I know that these 2 sides of this segment, FG and HG, are congruent. And from a previous lesson, we also know that when they share a side, we can use the reflexive property to say that side is congruent to itself. So I have all 3 sets of sides congruent, so yes, because of the midpoint and the reflexive property, I can say that triangle FGJ is congruent to triangle HGJ by side, side, side. Another shortcut is the side-angle side congruence postulate. If 2 sides and the included angle, and we'll talk about what included angle means shortly, of one triangle are congruent to 2 sides and the included angle of a second triangle, then the 2 triangles are congruent. Okay, so here I've got these sides congruent and then these sides congruent. So that's 2 sets of congruent sides. And the included angle means the angle formed by those 2 sides. So these 2 sides form angle R. And these 2 sides form angle U. So angle R is the included angle here. I can't say S or T is an included angle because it's not formed by these 2 sides. And I can't say V or W are included because it's not formed by these 2 sides. So R and U are the included angles. So if segment RS is congruent to segment UV, segment RT is congruent to segment UW, and the included angles, angle R is congruent to angle U, then I can say triangle RST is congruent to triangle, now let's get corresponding order, RST, UVW. So given that JN and LN are congruent segments, these here, and KN and MN are congruent segments, these here, is there enough information to prove that triangle JKN and triangle LMN are congruent? So I've got 2 sets of congruent sides. I don't know about this 3rd set, but I do have a pair of vertical angles. So I'm going to say yes, because of vertical angles, I can say that triangle JKN is congruent to triangle LMN by side, angle, side. Two sets of congruent sides and the included angles congruent. Next is the angle-side-angle congruence postulate. Okay, so if I have two angles and the included side of one triangle congruent to two angles and the included side of a second triangle, then the two triangles are congruent. Okay, so here's two sets of congruent angles, and the side that is between those angles, that is the included side. So if angle A is congruent to angle D, okay, then segment AC is congruent to segment DF, and angle C is congruent to angle F, then the two triangles are congruent. So triangle ABC is congruent to triangle DEF. Given the markings in the two triangles, is there enough information to prove them congruent? I would say yes, because I've got an angle here and here, side here and here, and then I've got vertical angles. And those vertical angles are congruent, so now I have two angles and the included side. So yes, now I can't write a congruent statement because I don't have letters on these triangles, but I can say yes, and why are they congruent? By angle, side, angle. One more shortcut for today. Angle, angle, side congruence theorem. If two angles and the non-included side, and a non-included side of one triangle are congruent to two angles, and a non-included side of a second triangle, then the two triangles are congruent. And this shouldn't say the non-included, it should say a non-included, because there are two non-included sides. So here I have angle A is congruent to angle D. Angle C is congruent to angle F. And a pair of non-included sides, segment BC, is congruent to segment EF. So there's my two angles and a non-included side, so there's a side that is not between the two angles. That is enough to say triangle ABC is congruent to triangle DEF. Given the markings in these two triangles, is there enough information to prove them congruent? So I've got a pair of congruent angles, another pair of congruent angles, and I have a shared side. So by the reflexive property, I can say that side is congruent to itself. That gives me angle, angle, side. So I would say yes by angle, angle, side. So now for each set of triangles, we have to determine if there's enough information to prove that they are congruent, and if they are, then write a congruent statement and give a reason that they are congruent. So here I have a 9, and here I have a 9. These are congruent sides. These are both 8, so they are congruent. And they share a side, so reflexive property says LK is congruent to LK. So by side, 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 I can say triangle JKL is congruent to triangle MKL. By side, side, side. AB is congruent to segment CB. So segment AB and segment CB are congruent. Segment BD bisects angle ABC. So here's angle ABC. Segment BD bisects it, so it cuts it in half, and that gives me congruent angles on either side of BD. And they share side BD. It is congruent to itself. So triangle A, not really sure where that J just came from. Triangle ABD is congruent to triangle CBD by side, angle, side. Segment BD bisects angle ABC. So just like we had over here, we have an angle bisector, so it cuts angle ABC in half. So these are congruent. And BD is perpendicular to AC. So BD and AC are perpendicular. That means that these are right angles down here. Now, right angles are congruent to each other. This is 90, this is 90. These two angles are congruent, so I have two sets of congruent angles, and they share side BD. So I can say BD is congruent to itself. So I have angle, side, angle. So it's two angles and an included side. So the answer is yes, they are congruent. So triangle ABD is congruent to triangle CBD by angle, side, angle. Okay, then here I've got a couple sets of congruent angles and vertical angles. So I have three sets of congruent angles. So I have angle, 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 but that is not one of our shortcuts. One of these triangles could be bigger than the other, but still have all the same angle measures. So for this one, I'm going to have to say, no, there is not enough information to say that they are congruent. AC and CD are perpendicular. AC and CD, there's a right angle right there. AC and AB are perpendicular, so there is a right angle right there. Point M is the midpoint of BD. So these are congruent. M cuts BD in half. There's also a pair of vertical angles. So what I have here is two angles and a non-included side. That is angle, angle, side. So I can say triangle ABM is congruent to triangle. Now I need to get corresponding order. So I have ABM, CDM. And that is by angle, angle, side. And last, I have segment AD is congruent to segment CB. Segment DC is congruent to segment BA. Then I have a shared side, AC, and I can say that is congruent to itself by the reflexive property. So AC is congruent to CA. So yes, they are congruent. Triangle ABC is congruent to triangle. So I've got ABC. Then down here I'm going to have CDA by side, side, side. In our next video, we will add one more shortcut. So we'll have the hypotenuse leg shortcut in our next video.